Hey students, let's run through some video solutions here. I think this will be a good learning exercise as well as self-grading to see how you did here. It says the terminals of the batteries have an EMF of 1.58. So here is our single cell battery, an alkali battery. It has an internal resistance of 0.125. So kind of in the diagram, I'm going to put a little resistor here and kind of mark it. Okay. I guess I probably should have put it inside of the battery. Internal resistance. It is connected with 22 gauge platinum wire. 22 gauge has a diameter of. When the platinum wire is first connected, the current, and so the current's going to run through this wire, and keep in mind I'm thinking of this wire as one big long resistor, okay? And it gives a current of 2.37 amps. Then, after a long period of time, the platinum warms up and to some higher, steady state, higher temperature, and the current drops down. Assuming at initial temperature of 20 degrees, what is the length? All right, well, starting with Ohm's law, current is equal to voltage divided by resistance. And in this case, we can think of it as two resistors, the internal resistance and then the resistance of the wire, which I'll just call capital R here, okay? And of course, the EMF, that is the voltage created by the chemical reaction, is the 1.58. So if that current comes out to be 2.37, we could then solve this for the resistance of that wire. So if I, let's see, I'll do a little math here, 1.58, and think about moving this over to here, 2.37. That would be what this denominator is equal to. Then if I subtract off the 0.125 for the internal resistance, this would be the resistance of about a half an ohm. Now, if we also remember the resistance is the resistivity times the length times the cross-sectional area, we know the type of material we have. It's platinum, and we know the gauge, so we can get that. And so ultimately, we can get the length of the wire because it would be the 0.542. And I'll bring this over for area and divide it by resistivity. Now, to do that, I guess I'll start my calculator here. I already got the resistance. So if I multiply by the area would be a pi times a radius squared. And the 22 gauge then has this diameter. So if I cut that in half, that'll be a 321 and make it millimeters and squared. All right, so if I take all that and divide by the resistivity, and here's where we're gonna use the little hint here back to our first chapter related to this material, chapter 27, let's see, 28, 27. Here we go. Table 27.2, and the resistivity of platinum is 11 times 10 to the minus 8. So if I divide by 11 times 10 to the negative 8, I should get a length of about 1.59 meters. Yay! All right, so there's A, if you will. What is the length of the wire? Now, doing the same logic, that is the current is equal to the voltage divided by the effective resistance, the equivalent resistance, that's the 1.25 times the R. This time, it warmed up. And that's going to give us then a different resistance to this wire. So let's see, the current now is 1.60. And going through that same logic that we just did in A, I've got my voltage, my 1.58 from the chemical reaction. Dividing it by this current here gives me a quotient of 0.9875. And then having that equal to this whole quantity, I can then subtract off the 0.125. And so now that it's warmed up, the resistance has gone up a little bit. Makes sense. Guess I should have put ohms here. To 0.8625 ohms. And so there's the resistance now that it has warmed up. And using the idea that the resistivity changes with temperature, which is what I guess this equation is all about. I guess it's 2719, that it's the original and then this temperature coefficient, this delta T here. And so I could then say, all right, the resistance, now that it's warmed up, is the original plus this alpha delta T. All right, so the warm temperature is the 0.8625, and the original resistance is this 0.542, 1 plus I. And here's where we got to come back here to the textbook here. Oh, pick up my mess I just made. Okay. And back to table 2. Here it is. And look at the platinum. And it looks like it's a 3.92 times 10 to the minus 3. So 3.92 times 10 to the minus 3, and then a delta T. All right, so grabbing my calculator here, I've got the warm resistance. Let me divide that by the initial resistance. Let me then subtract a 1, and then this is how much it went up. Okay, or percentage it went up. So it went about 59%. Now, if I divide that by 3.92 times 10 to the negative 3, I'm going to get my delta T. So delta T is about 151 degrees. And of course, it does say what's the final temperature. So this is final minus initial. And we'll take initial to be a 20. So if we add 20 on here, the platinum wire must be at about 171 degrees Celsius. Yay! All right, so hope I did that one well and hopefully without any confusion. Put that one off to the side. Let me grab the second question. Aha. All right, so here's the second question. And it says that we have a very long wire that has a current, and I'll just put here 13.3 amps, as shown in the figure. And then a second current segment, so it's just a little piece, which has a current of 8.25. So I'll put that in the diagram here. It has a length of 12.5 centimeters. Let me write that as 0.125 meters. So get rid of that decimal place. From the very long wire. The current in this segment is parallel to the current in the very long wire. So both of them have an arrowhead pointing up. Okay. What is the magnitude and direction? Maybe I'll start with direction of the magnetic force on this current segment. So the force, as we got out of chapter, I think this was 27, was that the magnetic force would be the current in the segment, times the length of the segment, cross the magnetic field. I guess mathematically, if we're just after the magnitude then, so the magnitude of the force is the current in number 2 times the length of number 2 times the magnetic field, and I guess it would be magnetic field at number 2, but it's created from the first wire, and then the sine of the angle between them. And so looking at that angle and the direction here, we would say that number 2 is in the presence of a field from number 1. And number 1, then, I would use what I've been calling right-hand rule number 2. Take my right hand and use my thumb for the current. So my fingers would wrap around, and using the traditional green, that would mean the field would come out of the paper over here on the left-hand side. But on the right-hand side, it would be going inward. And that's the part I care about. So it's going inward. And the current's going up. And so using the first right-hand rule for vector cross products, let me put my fingers in the direction of the current. So, okay, fingers up. Then I can adjust my wrist so that I can close my fingers towards the field. So it'd be kind of in this position. And so my thumb would be the direction of the force. So when it comes to direction, I'll just write they're towards each other. They're toward each other. They're moving inward. Now, that's not a surprise because that is section 30.2, where they actually go through exactly this problem. So hopefully this problem's pretty straightforward. Maybe I'll just turn the book over to chapter 30. Section 2. Here it is, and this is the equation I'm going to end up with in just a second. And they go on to talk about current, and they show this picture in the same direction that they attract each other here. And so directly attract towards each other is what it goes through the logic that we just did. So good. What I just reasoned out was the same thing that we just read about in section 2. And of course, that piece of the puzzle that completes it is to say, well, what is the magnetic field at wire number 2 from number 1? And this is the formula we have for a long straight wire. So this first wire is creating this much field, and it's A away. And so A is that distance between them, which says it is 1 1/4 centimeters. And of course, let's not forget that this is the angle between the current and the field. And as we drew in this picture, the current's going up and the field's going down. So that's 90 degrees. So mathematically, probably shouldn't try to squeeze it in this tight little space here, but I'm going to try it anyways, well, let's go down here. It'll look kind of funny under B here, but it's going to say here, the current in number 2, 8.25, times the length of number 2, this is the 0.125 meters, there. Mu naught is the 4 pi times 10 to the negative 7, the permeability of free space. The current in number 1 is the 13.3 amps. If I divide that by the 2 pi, and A being the distance between the two wires, that's going to be a 0.0125. There. And the sine of 90, let me not even write that in. That's just 1. In fact, I will save myself a little bit of calculating work by doing a little bit of canceling. And then we'll get the force, the magnitude of the force. So 8.25 times 0.125 times 2 times 10 to the negative 7 times 13.3 divided by 0.0125 gives me an attractional force of 2.19 times 10 to the minus 4 newtons. Yay! And so there's the magnitude and the direction. Now, B, as usual, it's a little harder. B says we have something very similar to A, but this time the current segment is perpendicular. So look at this picture to the very long wire. And the current flows away from the very long wire. So again, as the picture. But it looks like the segment still has an 8.25 amps. It has the same length, so it's got this 12.5 centimeter length. Its closest end, and so now the closest end is 1.25 centimeters. And so I guess the closest end being 1.25, but the furthest end, and not really drawn to scale in this diagram, is what we get. Let's see if we add one that's 13. So 13.75 centimeters is the farthest point of this. And you can kind of see what's coming up and why I'm making a kind of a numbers of where the beginning and the end is, because now we have this segment where the field varies, because the field depends on how far you are away from wire number 1. And when it's laid out this way, the field gets weaker as we go that way. So we need to have a deeper talk and a tougher problem. And since it changes, we've got some calculus we're going to have to do. What is the magnitude and the direction of the magnetic force? Well, why don't we do direction first again? So we'll here do direction. But going through exactly what we did in A, we would argue that in this vicinity, that is to the right of the long wire, the field would be going in. And close to the wire, it would be a strong field. And as we get further from the wire, it's weak. And that's what this math is saying here about the strength of the field. But the direction is always in. So if we now do right-hand rule number 1, doing this vector cross product, we would have to say, well, we're going to have to think about each little microscopic piece of this, because each little microscopic piece is going to have a microscopic different amounts. Even if you make them the same length, and even though they have the same current, they're in a different field. So that's where the calculus is going to come in. But again, all of these microscopic lengths are in the same direction, and the field is in the same direction. So as far as direction goes, they're all going to be in the same direction. And that would be, let's see, if I can kind of twist my hand this way. So my finger's in the direction of the current, and I close, that's going to get my thumb up. And so this is going to give towards the top of the paper here, kind of an upward push. So as far as answering the question about direction, there's an up. And so obviously it's got to be perpendicular to both the current and the field, which in this case would be up, whereas this case would have been along the horizontal axis. Okay, great. Now, as we said in terms of our calculus, why don't we change this little formula into its microscopic piece? That is, a little bit of force dF would be the current in that segment number 2 times a little bit of length of number 2 cross whatever the field is at that little piece of 2 created by number 1. And I don't think I showed you when I did this in A, but this formula is out of the definition of the magnetic field, which goes back here to chapter 29. And there's the I guess the two I'm looking at, looks like your author uses a DS and I just used a DL, so I should probably change that to a DS so I don't confuse you. But here it is if it's just, no variation, just simple non-calculus type of problem. But this is what we're going to want, calculus. And that's why we're going to do this integration right here, which I guess is very similar to what they did or the author did here in kind of this loop piece. Where he integrated along that loop. Although in this case, it looks like the strength of the field doesn't change, but the direction between it does. So it's not quite really the same problem as that example one. All right, so now that we already know the direction and every little section is going to be up, we could just say that the magnitude of the force, let's just call it F, is an integral of the magnitude of the cross product. So the magnitude of the cross product would be the magnitude of little current 2 times a little tiny segment. Again, let me change that to a DS. Times the field where the little microscopic piece number 2 is from A. And then the sine of the angle between them. And so as we look at this integration, we might say, well, the current in each little segment doesn't change. So we can pull that out in front of the integration. Now the integration ds is kind of along this wire, and just to kind of help my own mindset, since that wire is along a horizontal direction here, well, let me just call that a dx, kind of like that. Then the magnetic field is mu naught times the current in number 1 divided by 2 pi over how far away we are, and that would be, again, this x or the x value of where the current is. If we called x equals to 0 right here where wire number 1 is, then we are saying each microscopic piece is at some distance x and has a little microscopic length of dx. And in fact, that would also put our limits as we put here. This would be from 1 1/4 centimeters, but I'll write it as meters, to this 13 that we talked about. So 0.1375. Okay. And the last little piece of my integration is fortunately something that does not change and is actually pretty easy because it's sine of 90, which is 1. And so again, the current is always going to the right and the field is always going into the screen. So that is just a 1. So I'll just cross it out. And again, like any calculus problem, it's worth asking yourself what parameters here are constants and bring them out of the integration so that maybe the integration will look so complex. And sure enough, that's what we have. We just got this dx and x left over with our limits of 0.0125 and 0.1325. And so then we have current 2, mu naught, current 1 divided by 2 pi. And then this is ln. And then if we put in our limits of 0.1325 and subtract off the other limit, which then using the properties of logarithms, when you subtract 2 logs, you can write that as a quotient. I can then have a number here. So let's give this a try. Maybe I'll start with the natural log. All right, so there's the natural log, and I got 0.1325 divided by 0.0125. And there's that factor. Putting in my 2 currents, let's see, one of them was 8.25 and the other one was 13.3. Then times, and I'll make it a little easier myself. Remember, like we did up here in this one, this mu naught is a 4 pi, but when you have a 2 pi underneath it, it just reduces to 2 times 10 to the negative 7, making it a little bit easier to calculate. And then we get 5.18 times 10 to the minus 5 newtons for the force then from this long wire. Yay. And I think, and I hope that makes sense. Because, I'm sorry, I'm hesitating because I think I just copied this down wrong. I did. That's a 7, 5. Why did I do it? Oh, I did it here. Okay, so I did something silly here. So I guess I need to recalculate this, although that's not going to be much of a change. But let's give it a try here. Natural log of 0.1375 divided by 0.0125. Oh, yeah, so not much of a change, but slightly bigger. Okay. Then times, let me do the two currents. One is 13.3, the other was 8 1/4. And then the 2 times 10 to the negative 7 I was talking about. And, yeah, changed it right here, 2.6. So 5.26 times 10 to the minus 5 newtons would be the current from, the force there, and it would be up. All right. So, again, second one on part B, a little bit of calculus, or maybe even a lot of calculus. A lot harder for sure. So, I hope you got A for sure. And then let's hope you got a little bit of part B. And I'll say the same thing with number 3. You're going to see the same thing here. We got our straightforward kind of plug and chug problem here. And then one that's going to test our extension of our thinking, if you will, and apply our calculus to it. All right, so here we have a ring, and it says we've got this much current, flows in a circular loop, gives us the radius. What is the magnitude? So when do we need to do direction here? Of the magnetic field at this point P out here, that is 6.2 meters away from the center. Okay. And again, hopefully that looks pretty obvious. We did something like this in 30 with the Bips of Art. We did a, there it is. So we worked out, okay, what is it from a ring? It's like somewhere in here. There's the equation I'm looking for. Right here, what is the magnetic field from a ring? Where the A in here is the radius of the ring, and the X is the distance along the axis of symmetry. I is the current, and mu naught is the permeability of free space. So when I go to calculate this in A here, I'll just say B equals, and I got a mu naught I A squared over 2, and then I have an A squared plus an X squared to the 3/2 power. All right, so putting in our values, this is 4 pi times 10 to the negative 7. The current in the ring is the 5 1/4. The radius is 0.025 meters squared. Now there's the factor of 2. A is again that radius, 0.025 squared. And X is that distance out. Again, putting it in meters, 0.062 squared raised to a power of 3/2. Equals, and I'll just put the value right here. As far as calculator work, maybe I'll do the denominator, which is a little more complicated first. So 0.025 squared added to 0.062 squared, hit enter. I'll raise that to a power of 3/2 and multiply that by 2. So that's the denominator. Why don't I just hit the reciprocal key and then times everything across the numerator. And across the numerator then would be the 4 pi times 10 to the negative 7. Then the 5.25, then the 0.025 squared. And so 6.90 times 10 to the minus 6, or if we just want 6.90 microtesla. That's probably a good way to phrase it in terms of microteslas. Okay, good. Now, 3b is a lot like 2b, where we start with our general information, and now we got to think through it in terms of calculus. So this says, like part A, but now the current flows over the surface of a cylinder. It has the same radius. Now the length of the cylinder, L, is 8 centimeters. What is the magnitude of the magnetic field at X, which again is the 6.2 centimeters from the right edge at point P. So in other words, we basically have the same problem. It's just more realistic where you don't have it on a single ring, but the ring's been stretched out and quite a bit actually to 8 centimeters. And say, okay, what is this? And so the logic being that the field would be the sum of the field from a bunch of rings. And so this hopefully picture is kind of helping that you can think of each little microscopic amount of current as one ring. So each ring by itself doesn't really have much current because it's the same amount of current but now spread out. And so each microscopic ring, like I said, doesn't have much current. And these other rings are further away than this one. So I'm expecting to get a field quite a bit less than what we just got in A. Kind of like what happened back here in B. But we're going to do B here. Yeah, we expected the force to be quite a bit less because here in A, all the microscopic pieces were close to the wire, and here each microscopic piece gets further away where the field gets weaker, and so most of it is further away at a weaker field and therefore less force compared to A. And so sure enough, the force at B was much less than the force at A. So same thing here. I expect to get, a field, weaker. And let's see. Let's just see what happens. But maybe the best thing to do is to start off by saying what would be, a microscopic amount. And using this formula, I would say, well, think of these as a bunch of rings. Each ring would have a microscopic amount of current, di, in it. All the rings have the same radius, a squared, so nothing changes on that. And then this x is the distance away. And so that's going to be the part of this function that varies, because thinking of this as each ring, where x being from, this point P here to the ring, the first ring is going to be 6.2 centimeters away, and then gets a little further, a little further, a little further, a little further. So maybe I'll even put 6.2 centimeters is the closest ring, but then 14.2 centimeters, because I'm adding 8, is the furthest ring away. And so that's what my x is gonna vary. And of course, then I would say the field is adding them up. Now, that's not minor, but hopefully that has something to do with the direction. We weren't really asked explicitly about the direction, but using right-hand rule number 2, up here with the current going this way, that's kind of what that arrow looks like. I would curl my fingers in the direction of the current. And so if I'm putting a field here in green, it would point in that direction. And that's what these purple ones here are kind of showing, that it's going to go in that direction. I just realized, sorry, they're not the traditional green there. Don't know what happened, why I didn't use the traditional green. But same idea here, that each microscopic ring would make a field in this direction. So when you add them together, you don't have to worry about the X components, the Y components. That's nice when we have vectors that are all in the same direction. It makes adding them up much easier than having to do components. So in that sense, we're lucky. That's why I said maybe it doesn't need to be said, but it's not minor. We got to make sure that we're doing this right and that they, add up correctly. And we got to add vectors correctly. All right, now there is kind of this issue of, all right, how do I then equate or connect a microscopic amount of current with maybe a microscopic amount of distance? Because the logic in my mind here is that I'm adding up rings at different distances. And so, my question is, how is dx related to di? And maybe you see this in the idea of density. We've used it a lot, and we're going to continue to use it a lot. But we could call this like a ring current density, if you will. You could say a small amount of, maybe I'll just spell it out here, a small amount of current along a small length of the cylinder must be the same as the whole or all of the current divided by the whole or the complete length of the cylinder. So right here where we say small amount of current, well, this is what we mean by the di, a little microscopic amount of one little ring. And the length of that ring would be a dx, going a length in that direction. Whereas if I took the whole current, I, and divided by the whole length, L, this would be the mathematical connection that I'm after. What is that connection between di and dx? And so then I've got this mu naught. And in place of di, I can put total current over total length times dx. And so that's this di. I still have my a squared. I still have my 2. I got my other a squared. I got my x squared to the 3/2 power. Nice. And like we've said many times with all of our calculus, we go to do this, then go ahead and make things a little bit easier on yourself by bringing constants out in front of the integral. So it looks like downstairs I have the 2 and the L, and upstairs I have the mu naught, the I, and the a squared. And I'm still left with this a squared plus x squared to the 3/2. And then, of course, the limits now of my x are the 0.062 that we talked about earlier, and the 0.142, which was also talked about. Okay. U naught a squared I 2L. And now I'm going to take advantage of the little hint here. It says go ahead and use the integral tables. You could do this by hand if you want. This looks a lot like the one we did in class where we did a trig substitute. And those take a little bit of time. And so being on an exam and whatnot, I would encourage you to just, use the advantage of your book here and say, all right, where's my integral tables? And for our textbook, it's in Appendix B. It's open book, so you can use whatever book you want here. But it looks like in the second column of our integral table here, I think this is table, B5. down here, second from the bottom here, is the one we want. And there's the answer that we want. Okay, so this should be x over a squared. Actually, let me just double check. Is that the same thing? Something's bothering me about it. Oh, I guess these are ordered switch, but that wouldn't matter because it's addition, so it's commutative. Okay, and I have the square root of x squared plus a squared. And then, of course, I can evaluate it from 0.062 to 0.142. And this a squared cancels off. So I guess it'll save me a little bit of work. But now I need to put in my numbers. So this is 4 pi times 10 to the minus 7 for here. The whole current I believe was the same, wasn't it? Yeah, the 5.25. And that was the whole current, right? That came from, yeah, back here where we said this is the whole current divided by the whole length, yeah. And here's the 2. And here's the whole length, 8 centimeters, which I'm going to write in meters. And then this, I'll have to put in my limits, 0.142 over the square root of 0.142 squared plus the A. And the A is the radius, and the radius is the 0.025 squared. Okay, and then putting in this x, 0.062 over the square root, 0.062 squared plus 0.025 squared. All right, so not a simple one, but let's punch it in here to the calculator. And so let me do the 0.142 divided by the square root of 0.142 squared plus 0.025 squared, and then we'll end the first square root. Then I'll subtract 0.062 divided by the square root of 0.062 squared plus 0.025 squared, and that square root. Now let me just hit enter. That's this part. Then I can go times 5.25 times 4 pi 10 negative 7. Divide by 2 and also divide by 0.08. All right, so I get 2.37 microteslas. And we said we expected that to be smaller, by a reasonable amount. I might even guess more, but I think we're on the right track here. And so there is our 2 field calculations from number 3. All right, well, off to question 4. What did I do with my paperwork here for? We have some circuit stuff. And not that B is significantly harder than A, but we see the same pattern here. Really a straightforward one in A, so hopefully you get, good significant amount of the points here in A, and then, but also hopefully in B. But if we take a look at this top circuit to the right, what is the current coming out of the battery? And if you study this, you'll see that the current, as it comes out of this 5-volt battery, of course, it's going to split left and right. More on that in a second. But the stuff that goes right goes through the 60 and goes through the 40 And so these two are in series and are equivalent then by adding as 100 ohms. And so you can just think of these two as one. And once you do that, you can see the split is a parallel. It goes, some goes left, some goes right. So I have a 20 and a 100 that are in parallel. And so the equivalent resistance of all three of these would be the reciprocal of 20 plus the reciprocal of 100. And then taking the reciprocal of that is going to give me the equivalent. So these three resistors are equivalent to one resistor at 16 2/3 of an ohm. Which, maybe I'll just squeeze it in here. If you would want to get the current, you just take the voltage and divide it by its equivalent resistance. So this would just be 5 divided by the last answer, and we get 0.3 amps, or 300 milliamps. And so that's kind of what I meant by A is, I think, I hope you think, pretty straightforward. It wasn't really asking about each current individually. So all you had to do was find the equivalent, and we did, and stop there. You don't have to work backwards to find the current in each one. Whereas B is a little more complicated. We're going to look at this circuit and find the current in each one. And there are 4 resistors. You could take and put the 100 and the 400 in series, because whatever current is flowing through this loop here on the side, this branch, it's going to be the same. They're separated by a battery, so sometimes it's kind of hard to see that they're in series, but they do have the same current. They are in series, and you'll see it in the math. And maybe it's just as easy not to see it and just say, you know, I'm not going to use equivalents at all, because if I don't see these in series, then there's nothing else in series and nothing else in parallel. I can't, remember the series meant I can draw a line and go straight to the other one, and I can't do that for the 200 to anything, or the 300 to anything, or the 400 to anything, or the 100 to anything, other than going back around that way. So that was about the only thing I can say is the 100 and the 400 are in series. And then nothing's also in parallel. There's always something in between them. So this is where the other technique, the Kirchhoff's loop rule, comes into play, or loop, the KVL and KCL. So let's just do this. Let's just say that the current coming out of the 12-volt battery is I number 1. Comes along, it hits this node, it splits. Clearly, some of it goes around this way. The one that's kind of hard to predict is right here. Does the current continue on down because the 12-volt overpowers the 9-volt, and we're therefore charging up the 9-volt battery? Or on the other hand, does the loss of power going through this 100 ohm reduce it lower than this? And it doesn't go this way, but comes out that way. And hard to tell. And that's why I said you don't really make a real decision here on that one. You just kind of label it. So since I already put my arrowhead down, let me continue with that. And I'll call that 2 and that 3. Although, a little subtlety here is it has to for this to go this way, it's not just fighting 9 volts, but the lower part of the 9 volts is actually would be at a higher current if it was, a higher voltage if it was going that way. So, yeah. Well, I better not dwell too much. That's my point, is don't dwell on it too much. But I think if we analyze this carefully, we'll see it's going the other way. So let's not dwell on it too much. Let's just see what we get. But I would be surprised if that came out to be negative. In fact, maybe it's a good thing if it does come out to be negative, because at least when I'm doing examples for you guys, it's nice to, say, hey, it's okay if it comes out negative. You're not really needing to know what direction. The mathematics and the sign at the end of it will tell you. But I always encourage students to at least look at the picture, and, it just helps with your conceptual knowledge and your gut feeling and your understanding of the physics behind it on making the mark of the ones that are pretty clear. And so there's no doubt in my mind about 1 and 3. It's really whether 2 comes up and joins 1 and goes around that way, or did 1 split off and go this way. But 1 and 3, hands down, no doubt about those. Those are obvious. All right, so 1 and 3 are definitely going to come out positive. It's 2 I'm not real sure about. All right, and so here's what we do. We do the loops. We do the small loops. So let me just do the left loop. Let me start down here. And if I add up around this loop, I'd say, okay, plus 12 as I move myself from the small bar to the big bar. Then this is the Ohm's law. And since I'm going with the current, it's a negative, and the resistance is 100, and the current is I1. Then I'll go down this center branch here. This is where I go through the 9-volt battery, and I go from the plus to the minus, the big bar to the little bar, so that's a -9. Then I'm going with the current, or at least what I think is going to be the current. We'll see what comes out, but it still works mathematically for a negative current. But going with the current would be a negative, and Ohm's law would be 300 ohms times I2. Then we would get to this little branch, which we'd be going with the current. And to do that, we got to kind of remember that conservation of charge says, okay, if you're going to call this part of the branch I1, then this part of the branch also has to have I1, because what goes in there has to come out here, has to go in there, has to come out there, has to go in there, has to come out there. It's not until it hits a node can it split off and have a different number, because we can't lose electrons or gain electrons. That would violate conservation of charge. So here I know the direction and magnitude. It's, from right to left, and it's I1. So this would be minus 400 I1, and that completes the loop. And that'd be my first equation. Let me give myself a little room to simplify it. Equation number 2, then, would be this loop. Maybe I'll start down here. And so Ohm's law would be 300 I2. And I'm going from here up to here against the current, so it's plus. Then from little bar to big bar, so plus 9. And then around the loop, I hit another resistor, so that's 200 I3. That's the magnitude. And I'm going with the current, so it's minus, and that completes the loop. And I don't need quite as much room to simplify that one. It's a little shorter. And now that we've done the 2 small loops, don't do any more loops. I know there's a big loop, but the big loop mathematically is not an independent equation. It's just what you would get when you subtract these 2 equations. Subtract or add? Add, in this case. But the other one would be this node. And again, conservation of charge says what comes in must be equal to what comes out. So 2 and 3 come out, and number 1 goes in. Now, simplifying all these equations and putting all the unknowns on one side, I guess I'll write this as I1 minus I2 minus I3 equals 0. And writing this in matrix form, I would have this first line 1 minus 1 minus 1 equals 0. Now this equation, a little smudge there. I think that was a minus. Let's see, it was over here where we'd have to go minus 200, yeah. Why don't I leave the 9 on this side and then move the 300 I2 to the other side and the 200 I3 to the other side, and that'll change their sign. So this equation will have no I1, negative 300 I2, a plus 200 I3, and that has to equal a 9. This one, the 12 and the 9 make a 3. Here's the part of the math where I said you can kind of see it later on in the math that these two together are going to make minus 500 I1. And that's what we would have got if we said these two resistors were in series. And and again, in the math, you see it. They're just not right next to each other. And because they're not right next to each other in my loop. All right, so I guess I've done that term, and that term, and that term, and that term, and I'm only left with the negative 300 I2 equals 0. And maybe I'll leave the 3 on this side and put the 500 I1 on the other side, and the 300 I2 also on the other side. So that this would be 500, 300, 0 equals 3. Okay, so then if we reduce our matrix using the power of the calculator, which we'll diagonalize with our identity matrix, we will get our 3 currents. And recognize that when we fill in our box, 1 and 4 have to be the same. I guess that's an important step in this problem. All right, so grabbing my calculator here and going to my matrix and going to edit, I need a 3x4 matrix. And it would be a 1, negative 1, negative 1, 0, 0, negative 300, 200, 9, 500, 300, 0, 3. And now I can go quit. I do like to then sometimes just look just to make sure I typed it in right. 1, negative 1, negative 1, 0, 0, negative 300, 200, 9, 5, 3, 0, 3. Okay, good. So that's my matrix A. And so I want to do some math on my matrix A in the reduced row echelon form of matrix A is the operation I want to do. So there's the diagonal, and it looks like I get a 0.0135. There's the negative, 0.0125. So number 2 is going up here. And the last bit of current is 0.0261. All right, so the current in number 1 and number 4 would be 0.135. 0.135. And number 2 would be 0.0125, and maybe I'll just put up since my arrow has a down. I want to make sure that the person grading it knows that I knew it was up. The negative is fine as long as your arrow's down. Positive is fine as long as your arrow's up. I'm kind of readjusting it along the way, so I just want to make that clear. And then the 300 is the 0.0261. And a quick self-check would be then that these two are flowing together, so these two must add up to that, at least the absolute value of it. And sure enough, they do. So nice. Nice. Looks good. All right, so I've got my currents and everything seems to match. All right, now off to the last problem. And this is again another circuit one. This is the one where we close the switch and we got capacitors and resistors. Maybe this one's worth drawing or redrawing for a second as just a single capacitor and a single resistor. Because we did this single capacitor, single resistor one a lot. And so taking the equivalent of this, let's see, they're in series, so we add, so that's 600 ohms for the equivalent of those two. These are in series, but remember for capacitors, we do that reciprocal sum. So it's 45 reciprocal plus 35 reciprocal equals, and the reciprocal would give me a 19.7 microfarads for that. All right, well, I guess I haven't even read the problem here, but it just says study the circuit on the right. So I did. I looked at the picture. I replaced the two capacitors with its equivalent, the two resistors with its equivalent. It says, what is the current when the switch is first closed? Now, hopefully you remember on that when you are working with capacitors, if they are, when you're initially charging them up, there's like no voltage on them because there's no charge. And so when you are adding a loop, you get a 0 and a 0. It's like they're not even there. It's like it's just a wire. It's what we call it's a short circuit. So if you could imagine that capacitor not there and you just had a wire, a short circuit, you would just have your voltage, which is 20 volts. And you would be dividing it by 600 ohms. And that's the key to this one. And so 20 divided by 600 is 0.0333, or if you want, 33.3 milliamps. And so there's the first part of it. And B's not too bad either. Was kind of my way of saying you've had a long test, and so hopefully this is straightforward. But if you did go back to our derivation, we looked at charging capacitors and either looking at their charges or, in this case, their current. We said the current as a function of time would start here and taper off, and it would follow this pattern where the RC is referred to as the time constant of the circuit. And this is where our equivalence would come in. And so finding our time constant, our RC value, we would have 600 times 19.7 microfarads. And so 600 times 19.7 micro is, I'm debating to write that in milliseconds, maybe I will, is 11.8 milliseconds. And this problem is asking about a certain time frame here, right? It says how much time does it take for the current to drop down or reduce to 1/3 of its initial value. So we would write 1/3 of the initial value. And the initial value would cancel off. So whether or not you got A right or not doesn't really matter for B. But what does matter is the right time constant here. And so we've got this 1/3 times this E. That's where natural logs come into hand. If I take the natural log of both sides, I get rid of the E here on the right-hand side. And so solving this for time, I get minus the RC time constant, natural log of 1/3. And so putting that into my calculator, I get a negative, and I'll do the 11.8 milliseconds. So I'll put it in units of milliseconds. And then I have the natural log of 1/3. And it looks like I come out to be 13.0, and I'm in units of milliseconds. Yay! And that's it. All right. Well, hope you learned something. Hope you did well on the test. Take care, everybody.